This is Team 19088 presenting Mixed Reality System with Artificial Intelligence for Cardiopulmonary Resuscitation. The following is an outline of the presentation. First, our team poster. Approximately 475,000 people die per year as a result of cardiac arrest. 45% of cardiac arrest victims survive because of bystander-administered CPR. Through the use of mixed reality technology and an integrated sensor network, Team 19088 seeks to develop a CPR feedback device that will provide real-time performance feedback to increase the confidence of healthcare professionals and all emergency bystanders in their ability and preparedness to save lives. The design calls for a method by which to measure chest compression depth and frequency. The original design used an accelerometer. However, results were too skewed and unreadable due to signal noise. Through outside-of-the-box thinking, the team lead came up with the idea to use an ultrasonic sensor for the final design. This sensor uses sonar to measure distance between objects anywhere from 2 centimeters to 400 centimeters within a 3 millimeter accuracy. Previous designs have been based around virtual reality technology using the HTC Vive headset with Leap Motion hand tracking. This design limited the user to an exclusively digital experience and proved cumbersome since it had wired components and required an external power source. The current design incorporates the mixed reality Magic Leap headset, which allows the user to interact with digital assets and the physical world at the same time. The Magic Leap has an onboard power source, is Bluetooth wireless, and accounts for head, hand, and eye tracking.
So our project has a few major system requirements, which I'll go over. The first is the physiological accuracy requirement. The augmented reality system shall measure 2-inch compressions at 110 beats per minute with a tolerance of plus or minus 0.4 inches and plus or minus 10 beats per minute respectively. Next is the NLP accuracy requirement. So what we're requiring here is that the program be able to recognize when the user says certain key phrases, specifically call 911, as this was something that was specifically requested by our sponsor. Third is the software consistency requirement. The program will run with a streamlined processing unit that allows for a lag of half a beat with a tolerance of plus or minus a quarter of a beat. Last is the CPR standards consistency requirement. This is to make sure that the CPR depth and frequency numbers we guide the user towards are in line with standards set by the American Heart Association or the overseeing organization that are in charge of such standards. It is also the reason why we have the previously stated numbers in our first requirement.
Here we see our system block diagram. In this diagram, we have 5 main systems within our overall assembly. The user will perform CPR and receive real-time feedback from the feedback system, which displays compression data from the CPU. The CPU analyzes the data from the wearable, which is equipped with pressure sensors to enforce correct hand placement of the user, as well as an ultrasonic sensor to determine the depth of compression applied to the mannequin. This is our design concept and point design. The most important aspects of our design specifications are that the wearable must not be cumbersome, loose, or obstructive, low latency, and have a mixed reality medium for the user to interact with the mannequin. Here you can see some of our earlier concepts which used an accelerometer instead of an ultrasonic sensor to begin with. Here we see a requirement verification chart which includes our performance requirements, the method of verification, the limits and tolerances of our specifications, the measured value, and whether each requirement passed or failed. Firstly, we have 1.1, our physiological accuracy requirement. This was tested and passed. Our next requirement was natural language processing accuracy that we demonstrated and passed. Requirement 1.3 for quality was passed after inspection and demonstration. And finally, for 1.4, our software consistency, this was tested and passed. To continue with requirement verifications on the interface level, we also required that the NLP response be timely. This was tested and passed. For 2.2, our wearables, this functionality was demonstrated and passed. In our design feature requirements, we determined that the Magic Leap components, laptop, and mannequin must be in a set size and weight, which was analyzed and inspected for a passing mark.
Requirement 4.1 CPR standards and consistency passed as our system was created to account for a tolerance of plus or minus 0.4 inches and plus or minus 10 beats per minute. Requirement 4.2 realistic passed as our system contains visual and auditory stimuli. Lastly, requirement 5.1 power passed. The functionality of our project remains the same. We are able to measure the depth, frequency, and pressure of compressions while providing the user constructive feedback. The depth calibration had an accuracy within plus or minus 0.1 inches, and the compression pressure had an accuracy within plus or minus 0.108. Therefore, our compression data is quite accurate. The speech recognition portion rated at about an 80% accuracy. The deliverables to the sponsor include this video presentation, the final report, which includes the technical data package, and the code repository, which is on GitHub. Our physical deliverables will include the Magic Leap headset, the wearable glove, and the mannequin. This demonstration showcases the mixed reality environment. The user must say call 911. As the user compresses to the automated beat, it will turn red, green, or blue. Red means they're compressing too deep, green means that they're in a good range, and blue means their compressions are too shallow. This demonstration shows the wearable setup, which includes the Arduino breadboard, ultrasonic sensor, pressure pad, and the 9-volt battery. The CPR performance video shows a person with a full setup performing CPR. In the video is the wearable glove, Magic Leap headset, mannequin, and a makeshift stand. The other two clips display the compression depth and pressure data from that performance.
Throughout our work on this project, we learned a lot and overcame a lot of problems. For example, the original IMU design yielded too much error and proved to be an ineffective way of calibrating depth. To be able to use the ultrasonic sensor alternative, we added the new design for the lightweight plastic foldable. It is recommended to apply the mixed reality system for training and method exposure only, as the cord and the light pack might carry unnecessary risk into an emergency situation. By comparison to last year's project, however, the potential users increased with the change of the wearable design. In reference to the environment, our system uses a rechargeable modular 9-volt battery with a system platform that is open source for code development or optimization, and we have the database available for external system analysis or artificial intelligence as our sponsor was wanting. As safety concern, we have a very lightweight operation with an integrated sensor network for increased situational awareness, and all individual contact has compliant fabric or material, either with the headset or the wearable.